Okay, hello once again, and thank you for joining our workshop on getting started with Kumo's relational foundation model and how to predict user using your business data. I'm Kitty Ivanovska, and I will be your host today. In this workshop, you will hear from Yura Liskovac, professor at Stanford and co-founder and chief scientist at Kumo, and Matthias Fey, founding engineer at Kumo. Together, they will cover how to quickly connect your business data and start generating prediction with KumoRFM, real-world use cases like churn, fraud detection, and product recommendation, how to use KumoRFM, and how KumoRFM streamlines predictive workflows and accelerates experimentation. Before we begin, please remember to use the Q&A section to ask any question throughout the session. At the end, we will dedicate time to answer your question live. And now I believe we are ready to start. I'd like to invite Matthias to begin this workshop. Matthias, if you're ready, you can start. Over to you.
Okay, thank you, Katie, and welcome everyone. My name is Matthias, and I'm machine learning lead behind KumoRFM. And today I want to especially talk about how you can use KumoRFM for your own apps, for your own use cases, and how you can add predictive power to all your different applications. So for this, we want to start with a demo. And I prepared like a super simple Streamlit app, which builds like a fashion shop, which a use case that comes up frequently. And we want to use KumoRFM to extend this fashion shop here by predictive power, by making it more attractive to users. So we're starting with that. And so this fashion shop here has like the basic functionality built in. It has like, it welcomes me. Hi, Matthias, welcome back. It has a home screen. And then it has this sidebar navigation here that groups clothes by the categories like dress and trousers and sweaters and t-shirts and so on. And I can order these sweaters simply by clicking on them. And I can inspect my own past order history by looking at this past order view here. And you can see the sweaters I added here are appearing. And I also have a return view, like a view of returned items I ordered but returned later on. And so this shop here works, but it's kind of like super bare bones. So I want to start with adding KumoRFM to that. So on the right here, you can see my my editor. I quickly want to go over the code so that it's easy to understand. And so I'm basically now user ID 50 in this demo, and all the data I'm working on is prepared here as a set of pandas data frames. So I have users, I have items, and I have these interactions between users and items, such as views, orders, and returns. So I load this data into memory here and basically save it into my session. And so I set up the sidebar, I set up the title, which is appearing on the left view here. And then for all these different views, I have specific view logic, like the home screen welcomes me. The return view basically loads in the returns data frame. It filters the return data frame by my own user ID so that it's only holding the data that I'm returning, or like of the items I have returned. It sorts these values by date, and then it basically has some logic to visualize that by just simply iterating over that. And I have similar logic for like past orders, but instead of loading the return data frame, I'm loading in the orders data frame and filter it by my own user ID. And then lastly, I have these views that show all the items I have according to categories. So I'm loading in the items data frame here, but then I'm filtering these items by their product type name and iterating over them and visualizing them. I have some special logic for clicking a button here and ordering an item, and that would mean that I now append a new order into my orders data frame. So I want to make this shop here a bit cooler. So we can directly start by just typing in from Kumo AI experimental import RFM. And so this is our Kumo SDK. And the RFM logic here is under the sub-package experimental because the API is subject to change, but it's still fully functional and quite robust. And so you can simply install this package on yourself. So, but if you want to use it in like a Streamlit app, for example, then we need to make this model available here in this app. And so what we can write in this case is that we cache a new resource, which we call load model. And that load model function basically takes in the data I have available. And in my case, this would be the dictionary of pandas data frames. And I want to return it a new KumoRFM model. What I need to do now is that I need to initialize the RFM package to the backend. And I can simply do that by calling rfm.init. And then I can create a graph out of my set of pandas data frames, which basically describe their relationships together. It describes the primary keys, the time columns, the semantic type, all information that is needed to use this data and process it via neural networks and relational foundation models. So what I do here is that I create a local graph because it's in memory, and I can simply pass in this dictionary of pandas data frames, and this will automatically infer all this information from me. And what I do then is that I can finally initialize my model by simply passing this graph into this. So this is all I need to make KumoRFM ready. And so the first application or the first use case I'm interested in is making this welcome page here a bit, a bit more attractive. And one thing that usually people do is that they recommend items to users that they are likely going to buy, and they recommend items items people may want to rebuy. So I go into my view here of the home view. And I can simply perform like a link prediction task or recommendation task using KumoRFM. So what I do is that whenever I haven't computed something, so I write that the session state I'm interested in is empty. And then I can simply load my model here and pass in the newly refreshed data. So once I save, you can see that Streamlit app refreshes. And below here in the console, you can see that everything is successfully set up. So the graph was correctly inferred based on primary keys and time columns. It has rich links in between them. And the graph has been basically constructed. It holds over 1 million nodes and over 5 million edges. And everything is set up and ready to go. So I'm now basically, this is all I need to do to now be able to start querying this model. So I'm ready to start write a query, which we call a predictive query, which is like a SQL syntax, but instead of querying the past, we are basically interested in the future. So our query starts with a predict clause. And in our case, for recommendation task, we are interested in the item IDs of all the future orders I will do in the next 7 days. And this is based on the list distinct application. So I'm interested in finding out all the items I will likely going to be purchasing in the past. And I'm not interested in all of them. I want to rank them. So I'm interested in the top K. And now I need to specify for which user I want to generate these predictions. And in this case, I can simply write for a specific user, and that user is me, the user ID I saved previously in the global variable. So I have my predictive query. And what I can do now is that I can simply pass this query into the predict function of the model. And if I print this now, this should hopefully work. You can see here that the predictive query was executed in 1.2 seconds. It generated a link prediction task, and it gave me predictions back or recommendations back. So you can see that I received predictions for the entity 50, for a specific point in time, which is today. And then I got a list of classes back, and the class here basically means the item ID I'm recommending here. The last column here indicates the score, which means the likelihood that I'm going to purchase something, this item here, accordingly. And so this works. This works. And so now I want to visualize that. So I'm taking this prediction and I'm merging it with a set of items so that I can display these items. So I'm performing a pandas merge. And so I'll take in from the session state the items data frame, and I merge it with my prediction. Especially, I only need the class column here. And so I'm merging this with a right join. And on the left side, I want to merge with the item ID column. And on the right side, I want to merge with the class column. And so now previously that we want to have two views. One would be for new items I get recommended, and the second view would be around items I'm likely going to rebuy. And so this list distinct query here doesn't differentiate between the two. It just lists you all the things you're likely going to buy next, independent of whether they are new items or repeated items. And so I can easily filter this my own. So I'm now taking in the order data frame, which is stored in the session as well. And I'm filtering this orders data frame by the user ID of myself. So I'm taking the user ID and compare it with myself. And then all I need to do is that I need to check which of these items I get recommended is in my past orders as well. So I'm creating a mask here, and true means I have purchased this item in the past, and false means this is a new item for me. And so I can simply now store this information into my session as well. So recommended items would refer here to all the items that are new for me, and I'm storing the top 3 on there. And I can also store all the repeated items, which would be where the mask is true, and I'm storing the top 3 there as well. So once I save this, this predictive query gets regenerated, but it's now stored in my session. And so now all I need to do is that I need to displaying these items here. So whenever I have something in my session, I can simply display these items. So I'm taking all the items I have from my recommended items, and I say something like, here are a few things you might like. And this needs to be this. And then I have a button such as order now. And so hopefully this works now. Let me quickly restart. Something went wrong. Oh, I'm missing this one here. Sorry. Perfect. Okay, this is my first view. And for my second view, I can basically do the same, but I'm inspecting the repeated items. But instead, here I say, left it once, love it again. So these are all my items I previously purchased. And instead of order now, I say buy again. And so these will now appear here. And so if I check these in my past orders, then I can see that I find this trouser here, and this trouser here, and I can also find this sweater here. So this is super cool because it now gives the user something where it can directly interact with the platform instead of going through like a search search functionality. The next thing I want to add is that I want to add churn predictions to my app. So whenever a user hasn't purchased something in a long time and is about to churn the platform, I want to give them a coupon to be active again. So I can easily achieve that with KumoRFM as well. So I'm saying whenever I haven't computed anything for churn, I now load my model again. And this time I'm writing a churn predictive query, which would be here, predict the number of counts or the number of orders I will place in the next 30 days. And I don't want to predict the orders I will do, but I'm rather interested in whether I'm doing 0 orders in the next 30 days. And again, I'm interested in this prediction for myself. So user ID, user.user ID equals 50. And so I can again pass that to my model. And we can simply save this and look whether that's computed correctly. Here we can see the predictive query got executed successfully. It was detected as binary classification task, and the model predicts that I'm likely going to be churning with a probability of 0.272. Once again, I can just save this in my session state. So I'm going to save this into churn. And all I need to do now is that I can say if churn is in my session state, so I have this computed. And importantly, I only want to display a message if I'm going to churn. So I can say if the session state of churn with a true probability that I'm going to churn is greater than 0.9, we say something like special thank you. Click here to receive your $10 coupon, or we can make this 100. We are friendly. So once I save that, we will see nothing. But if I change this now to 70% likelihood, then you see that this appears here for me. Let's put it back because 70% is maybe a bit too low. Okay, the last use case I quickly want to showcase is around the returns view, and especially I want to predict whether I can identify the reason an item was returned. So I'm going to my return view, which is here. And I can once again say then I want to do something on the modeling side. So I can load the model here once again and compute something for the session state.reason. And so this time I'm interested in making a prediction for a set of items. So I'm getting the return IDs of all the items I have returned. And this is directly accessible for me by looking at the returns data frame. I'm looking at the return ID and simply converting that into a list. And so the query I'm now interested in is predicting the reason an item was returned. And I want to do this for all the return. I want to do this for all the returns with where the return ID is in my list of return IDs. So that means I'm writing, I need to pass a list here in my query, which would be a list separated by a comma. And then I'm saying I don't want to join this list of return IDs here, but importantly, I need to convert them into a string first. And so this should hopefully work. And so we can run the model and simply print the prediction here just to make sure. There's a small issue. Forgot this one. And forgot this one. So, okay, so you can see here in my console that the predictive query got executed, and it actually predicts these for these 3 return IDs here that belong to me. This is a multi-classification task, and so it gives me a prediction for each available class for each entity. So I have 5 different classes here, so I'm receiving a list of 15 rows, with the highest marking the one that is most likely. And so we can just save this now into the session state, given reason. We can execute again. Session state, not date. Everything works. And now all I need to do is basically visualizing what was just computed. So I'm going into my view field and say if this reason is in my session state, I can visualize that, and I can visualize it using a select box, for example. So I'm getting all the different options from my reason state, and I look at the class in particular, and I convert them into a list. And then I need to basically compute slices of 5. So I'm doing a bit of a hack here, but just say 5 times e from the start and 5 times e plus 1 to the end. And then I can say I want to visualize that as part of the select box, where I can say reason, and then I list the options here, and I need to pass a p for this select box. And so once I save that, you can see that this select box now was created here, and it actually predicts the different reason why an item was returned. Users can still change this here, but it's sorted by likelihood, so people do not have to change long to find their reason in the best case. And so this is basically the demo I wanted to show, and that shows basically how easy it is to integrate KumoRFM into any possible scenario. The one question you may have is that, okay, you've seen that now, and then you say, oh, this might not, just might give you random numbers. And so I want to bake this up because KumoRFM also provides an evaluation mode. And this evaluation mode is used to identify the quality or the output of a particular predictive query. And so I've created this Jupyter notebook here. I can make it a bit larger. That basically replicates the setup I showed in the demo. So I'm reading in the data here. I'm creating the graph. This would be the graph visualization of this data, where I have the users and the items, and they are all connected differently to these fact tables here. I put that into the KumoRFM model, and then I can run all these different predictive queries as well, but instead of saying model.predict, I'm saying model.evaluate. And this will basically go back in time to a timestamp where we can compute labels for all the entities we are making a prediction for. And then it will select a subset of entities to make a prediction for. It does this prediction, and then it computes metrics on top. So I can simply use this link prediction query here and say dot evaluate. And you can see that this was evaluated on 400 different test examples, because that's the number of entities I have in my data set that made a purchase in the last week. And then it gives you all the different metrics here you can think of, like mean, average, precision at different thresholds, precision, recall, F1, and so on. And so we can repeat this for all the different queries. So for the churn predictive query, this would be a binary classification task. So I'm getting binary classification metrics, such as average precision or AROC and so on. And you can directly see how good that model or this predictive query is performing on your data. Importantly, you can also tune that performance. So we're providing different run modes. And by default, we're choosing a run mode that has a good trade-off between runtime and model performance. But if you're just interested in the best model performance ever, you can pick up this run mode best here, which uses more context, and it uses a better model internally to improve the performance. And here in this case, we are able to improve all these metrics slightly. The last query was the return reason, which was a multi-class classification task. And by default, it gives us the accuracy of that, which would be here 0.54. Which is, in my opinion, quite a good accuracy for the return reason. But most importantly here, you can also tune the set of metrics you're interested in. So we can not only compute accuracy, but you can also say, give me MRR back. And once you execute that again, you also get that metric here. So this is like a quick way to validate that your predictive query is functioning as expected and delivering good results. If you need something more than that, you can also imagine that you're just running your predict command in a for loop over a set of items. So for each predict command, we are supporting up to 100 entity at a time. And so what you need to look out for here is that you can run for all your users. You select the given user IDs by slicing. You format your query correspondingly, and then you're putting this query into the predict function, but you need to manually go back in time in order to get predictions from an earlier snapshot. And then afterwards, you can simply concatenate your predictions and compare them manually with your ground truth labels. This is all from me for now. Thank you for your attention, and I'm giving it to Yuri to give a bit of more technical details around KumoRFM.
Thank you, Matthias. This was great. And I hope that this demo showed how easy it is to basically put predictions into production, into a new application, without any model training, without any feature engineering or anything like that, right? So what we have demonstrated is a pre-trained model for machine learning, right? And these relational foundation models that we have built are basically filling a big hole left by LLMs, right? LLMs are predicting text from text, but KumoRFM is predicting outcomes from business data. And just like LLMs replace time-consuming and difficult and expensive natural language processing work, RFMs replace time-consuming, difficult, and expensive predictive modeling work, right? And since RFMs fill this hole of basically having a foundation model for business data, this means they are not competing or replacing LLMs. We think that in the future, basically RFMs and LLMs are complementary to each other, so most businesses are going to use both, right? So what RFM is able to do is something that LLMs cannot. It's really a foundation model for business tabular relational data and allows you to get accurate predictions without any model training out of the model. What I want to do next is tell you more about how we built this pre-trained model and how does it work, right? So basically, we have a foundation model for predictions, something that was not possible to do before. And maybe the best way to build an analogy is to build an analogy with large language models, right? In large language models, we point them to text, unstructured documents, we write a prompt, we ask a question, and then the model does, let's say, this kind of human-like, common sense, in-context reasoning to give us textual output. How KumoRFM operates is in some sense similar, but different. You point it to your business data. So in Matthias's demo, we saw that we had this set of pandas data frames. We had a customers table, we had a items products table, and then we had users buying products, users returning products, and users clicking on the products. And that was kind of the schema, and we said, this is our data. Then we prompt the model with this predictive query that says, give me a given prediction, right? And Matthias demonstrated that this predictive query can express recommendations, can express classification, regression, anything you like. And in a single forward pass of this pre-trained model, we obtain accurate predictions, right? So that's kind of the magic, is that we get machine learning without any task or dataset specific model training. So how do we use KumoRFM? We essentially point it to our business data, to our set of tables. We prompt the model to specify a specific task, and in less than a second, we get returned the prediction that is specified by the task. Our benchmarks on data sets that the model has never seen before is that we get accuracy that is comparable to manually built models. Manually built models take days or weeks to be built. Here, we get the same level of accuracy in 1 second, right? So truly, now we democratized access to machine learning. It's super easy to integrate predictive AI into your applications. No PhD in machine learning is needed. You save tons of time and get high accuracy. Maybe now to go deeper into how KumoRFM works, is the first thing is that KumoRFM is a pre-trained model, right? Usually we think of machine learning as we collect the training data, we train the model to solve a specific task, and now we put that model in production. And it usually takes months to collect the data, train the model, and then put it in production. KumoRFM has been pre-trained, which means that no training is necessary. You simply point it to your data, you specify the task, you prompt the model with your task, and you will immediately get out predictions basically by a single forward pass of this pre-trained KumoRFM model. KumoRFM is based on the relational deep learning, right? And the way this operates, if you want to learn more, I have a link to the research paper posted here. But the way this operates is, if I have a set of tables, let's say in my case, I have my customers, I have my products, and then people buying products and people viewing, clicking on products. Then the RFM Kumo will basically take this data and internally represent it as a graph. So every user becomes a node, every order becomes a node, every view becomes a node, and every product becomes a node. And all these nodes have attributes attached to them, which is, for example, for a product, this would be image, description, name, color, weight, size, and so on. And then imagine now that when we write the predict statement, we really say that we want to make a prediction about a node in this graph. So maybe we want to make a prediction whether, what will be the lifetime value of this particular person, or whether this particular person is going to churn. And generally, if we want to predict whether somebody is going to churn, we would need to do a bunch of feature engineering, giving us some sense about users' activity in the past, what they purchase, how much they purchase, and things like that, and hope that those features predict their churn activity. Here, with KumoRFM, we don't need to do any of that. We just point to this relational data, this set of tables, and now we are able to make a prediction over it. And the way the RFM operates is that it looks at this data as a graph. So when we are making a prediction about this particular person, we are going to learn from all the activity of this person, all the views, all the purchases, all the properties of this product that the user has watched and the user has purchased. But then we can continue kind of exploring in this graph. So now from these two products, we can go back to the left, and this means that we are now going also to learn from other activities that other people have done on these two products, and we can basically recursively expand the graph. So if I take this, then the way I can think of this is that basically I have a neural network architecture called a relational graph transformer that basically tokenizes this subgraph around the entity of interest, and then the attention mechanism can now attend over this entire graph to basically learn or capture what signals predict whether somebody is going to churn. And the point is that rather than us manually joining tables and saying, oh, how many purchases did you make in the last week, and so on, and doing feature engineering, here the attention goes over the raw events, so it can learn at much higher fidelity, which means that graph transformers basically attend across multiple columns, multiple tables, multiple hops away. And this means that the attention mechanism can learn at much higher fidelity, at much higher kind of level of detail than manually kind of generated features that are kind of some summary statistics of the data, very, very crude, very clumsy in a sense, can do. So that's the key idea here, is that basically we can attend over this graph, and this graph spans multiple hops, and kind of we can make a prediction from attending over this set of events and a set of products and a set of other events from other people, and so on and so forth, to make that prediction. So now, what is KumoRFM? It's a relational graph transformer that has been pre-trained ahead of time. The architecture has two main components. There is a table invariant row level encoder, because the model can be applied to different databases, different tables with many different columns, including text columns, embedding columns, image columns, and so on, as well as different types of schemas. So the first hard thing to solve is, how do we encode a row in a table that is agnostic from the data types in the table, as well as the number of columns in the table. And then the second part of this architecture is the relational graph transformer and the in-context learning, so that we can basically, in a single forward pass, the model is able to make an accurate prediction from the in-context learning framework. So now, how do we specify the task, right? How do we specify the task? How do we, in some sense, prompt the model? We have developed this declarative language for task specification that we call predictive query. And the point is that predictive query has this predict statement followed by the name of the entity that we want to predict for. So we say we want to predict this value for this type of entity. And the language is SQL-like, so it also has SQL-like operators. I can predict count, I can predict sum, I can predict lists, and so on and so forth. So this really means that I can say, predict me whether the count of transactions in the next month is going to be greater than 0. And that's a churn model. I can say, list me all the product IDs the customer is going to buy in the next 60 days. And so on and so forth, right? So really, I simply declaratively specify the task. So what is happening behind the scene? What is happening behind the scene is that your data gets represented as a graph. And then once you specify the task, we essentially generate a small set of in-context examples together with their labels that are then sent to the foundation model together with the unlabeled example to give you an accurate prediction. So what do I mean by this is, for example, if you say, I want to predict whether the count of transactions, next month is going to be 0 for a given user ID, for a given customer ID, we are going to sample a number of different customers in the data. We are going to look 1 month back and see whether those customers in the last 1 month have churned or not, so that we can generate this 30-day forward-looking label. And then we are basically going to take their contextual subgraphs plus their label as a part of the in-context set of examples. We are going to take the customer for which you want to make a prediction today, whether they're going to churn or not next month. And the model will then, based on this set of in-context examples, you can think of this almost like as a small labeled kind of learning or training data set. The model is going in a single forward pass, give you an accurate prediction. So that's what is going on internally. The model not only gives you predictions, but can actually give you explanations. The way the model gives you explanations is that we can trace the attention mechanism back to the raw data, back to the raw columns and the raw tables, and tell you what columns, what tables were important for the model to make a given prediction. Again, all this is done with a pre-trained frozen model. All this is done in real time. Now you might be asking, okay, but how accurate this really is, right? This seems kind of, it doesn't seem to be, how can you make accurate predictions if you haven't really trained on my data set, if you haven't really trained on the tasks I care about? So we had the same question, and we did a very thorough benchmarking using the Stanford RelBench benchmark, where we have a set of 7 different relational databases coming from many different industries and about 30 different predictive tasks. And we benchmark this against kind of tree-based methods, against kind of manually data scientist built models, against graph neural networks, as well as against, like a 3 billion LLM where you just go and ask it and it gives you an answer. And what do we find is quite interesting. First, what we find is that KumoRFM is on par with best baselines across a number of different data sets and without any fine tuning. So the model has never seen these data sets before, was never trained on these data sets or these tasks before, but still only within context learning, it gives us very high accuracy. If we further fine tune Kumo for these data sets, for these specific tasks, then we get further boosting accuracy. This was for classification, like binary classification, multi-class classification, and things like that. The model is also able to do regression, and we see the same thing here. Basically, favorable comparison to so now this is error, so lower is better, to tree-based methods, to manually kind of feature engineered built models, RDL, in-context learning, fine-tuning of the foundation model. So this is now the regression type tasks. And of course, also in terms of recommendation, again, here, higher is better. We see very favorable comparison in terms of the quality of recommendations as opposed to alternative approaches. Of course, we are very interested for you to try this out on your own data sets. And let us know and give us feedback for us to understand where does this work, what is in distribution, what is out of distribution, and so that we can further improve these foundation models. I would really encourage you, because today we are making KumoRFM publicly available. We are releasing the SDK, so you can now try this on your own data, basically for free, and see how this works. Give us feedback so we can kind of further keep improving these models and really democratize, let's say, machine learning predictive intelligence, and kind of I would say fill this hole that the LLMs have left, right? LLMs are great at common sense, human-like reasoning, but they are not able to make accurate predictions over business data. That's a big hole. So now with this foundation model, we are able to fill that hole in. And of course, right, what's the benefit? The benefit is that now basically you don't need to create training data sets. You don't have to build models. You don't need to train models. You can just ask the foundation model for the prediction and you will get it immediately. So in terms of the time to value, we go from weeks or months to essentially a second or two. So that's the big unlock here. So to finish my part, what is KumoRFM? It's a foundation model for business data. What can it do? It can make accurate zero-shot predictions over your business tabular relational data. Can I make the model even better? Yes, you can. You can fine-tune on your data on your specific task. Why does this matter? Basically, we are now commoditizing predictions. Predictive models are now democratized. Anyone can write a predictive query and is able to put kind of the predictive intelligence inside their applications, inside your own agents, and really use the value of your own data that you have to allow to make kind of better decisions, to build applications that are personalized, that are even more delightful to use by the users. So this completes my talk, my part, and I will hand it off to Matthias to now give you a quick overview of how you can get started and how you can use this for your own tasks, for your own work.
Okay, thank you, Yuri. I'm quickly wrapping it up so that we have enough time for Q&A. And so, yeah, we are releasing KumoRFM, bring your own data today. You can simply pip install it, and all the instructions you can find by visiting KumoRFM.ai. So this has full support for Google Colab, Jupyter Notebooks, your IDEs, and it doesn't come with blurred dependencies. Only NumPy and Pandas are required. So if you browse KumoRFM, you will see a quick start guide that basically walks you through on how to set everything up. This is super similar to what I showed in the demo. Most importantly, there's this button here on creating an API key. So you can simply type in the name and your API key will be created. In addition, we provide Google Colab, which contains all the Python syntax and so on in order to interact with KumoRFM efficiently. So this is a must read if you want to get started quickly and learn or love to learn while going through interactive code examples. So I want to use a bit of time to explain how the KumoRFM package works, because I also see questions around what gets actually sent to the model and so on. So KumoRFM is designed in such a way that most of the work is actually done on the client side. So we currently expect users to hold a set of pandas data frames in memory. And then based on these definitions of pandas data frames, we define a graph out of this. So this means what is the primary key, what is the time column if it exists, how a foreign key is defined, and so on. And so this definition together with the data goes into what we call the graph materialization phase, where we construct edges out of that and we kind of sanitize the data. So that means we remove duplicated primary keys and so on. This process is fully in memory, but it will not load up your memory. So if you can load your pandas data frames into memory, then adding this graph materialization step has little to no overhead. Next, you can then write your predictive query or query the model. And so this string of a predictive query goes into a parser and validates on the backend side and confirms that everything is correctly defined. And then the most important step, the context generation, like what is the context or the in-context learning examples we create. This is also done on the client side. So that means we are querying the graph in a forward-looking fashion to find the labels of context examples. And then we also run it in the backward fashion in order to construct subgraphs. And so only this context here is then actually sent to the model and will be executed on the server. So we never will, and this server here is completely stateless. So it just contains, gets the context, gets a prediction, and forgets about everything else. So, and then lastly, I want to give a quick tips on what is the best way to get started and what to look out for. So we have this inference logic that infers graphs, infers primary keys, and so on. So this was tested quite excessively, but it still cannot be guaranteed that this works in 100% of all cases. But most importantly, you can change everything that was inferred. So you can change the semantic type of a column. And semantic type here means like the type of data, which is important to look at from like a model processing perspective. You can change the primary key, time column, and all the links of your graph. So this is just a good sanity check to do. Just confirm that everything is defined in the way it should be before moving further. And then a few quick tips to get to good results as soon as possible. So if you have your data up and ready, I feel like trying to get to a predictive query as soon as possible is like the best way to find success. So limit yourself to a small number of tables. Don't add 12 tables to your graph immediately. Start with 1 or 3 and then progressively add more as you go. But usually 1 or 3 tables, like the most important tables, are the most important one to get going, and do not lose time on all the others. And then the semantic type definition of columns is pretty crucial in order to let predictive query identify the correct task. So you may find yourself having a user age column and want to predict that, but this user age column can be either treated as a regression task or a classification task, depending on the semantic type of the age column. So if your predictive query may throw like a warning or an error or may identify a wrong task type, then it's good to go back and revisit the semantic type of this column. And lastly, make sure that critical information is reachable from your entity. So if you have like what you feel is like a super strong signal table, but it's like miles away from your entity you're making a prediction for, then this might be something to look out for and improve. So you have two options, like bringing this table closer to the entity you're making a prediction for. If that doesn't work, tune the number of hops we sample for context generation. But this will have an upper limit as well. And then once this is all done, go explore more advanced settings, such as like the run mode option I introduced, or setting a specific anchor time to do holdout set evaluation or predicting at a fixed timestamp every day, and so on. So these are like my best tips I could think of, but I'm super excited that you will try it out, and please let us know what you think. You can get a KumoRFM API key for free and start building with your data immediately. Check out our Quick Start notebook, and if you have anything to share and build with KumoRFM, please let us know. Thank you for your attention.
Yeah, thank you so much, everyone, for joining. Maybe just to emphasize, what you have just seen is a free version of our KumoRFM, which you can basically download the SDK and start playing with it. All the data, that your data is stored locally on your machine as part of the SDK, and then the only thing that gets sent to the Kumo servers is the in-context examples to get back the prediction. And the server is stateless in a sense that none of that data is being saved. It just goes directly into the GPU and the answer comes back. Of course, in terms of the data sites that this supports, it supports as big data sets as the machine that you have locally. So if you have a machine with 12 terabytes of memory, you can support data sets that are up to 12 terabytes large. So that is not a limitation. If you require kind of more support, more throughput, bigger data, and things like that, you're always welcome to reach out to us, and we can talk about our kind of more advanced commercial offerings that you can also try out. I think this concludes our webinar. What we are going to do next is to answer the questions that are in the Q&A. So if you have a question, please put it in the Q&A. And we are going to answer them with Matthias. Matthias, you want to pick your favorite question, or shall I do one and then you do the next one?
Please go ahead if you have one.
Okay. Just, I think there are questions, for example, by Nelson about what considerations are there for data security. Does your data get sent anywhere? As I said, your data is only stored locally. What gets sent to the Kumo server is kind of binary encoded subset of the in-context examples, so that you can get the response and get the prediction. Matthias, now you can take one.
Yeah, I see a lot of questions related to time series forecasting, which is probably also related to our graph transformer for time series forecasting. So it's possible to do time series forecasting in KumoRFM, but you can actually do it with multiple predictive queries. So what you can do is you say, predict me the series for the next day, and then predict me the series for the day after, and so on. So this elegantly defines like a problem of time series as well, and this should perform super well. So we are also having like support for time series forecasting in predictive query. It's not built in yet into KumoRFM, but this is something we want to add pretty soon.
Yeah, I can also answer Ben's question about persisting the graph and the scalability for massive graphs. The offering that we demonstrated today, you could persist the graph locally, but the enterprise version of Kumo allows you to persist the graph and support graphs with tens of billions of nodes, and you can truly use these models to put them in production to improve your production use cases across a number of different domains.
There's one question on the prediction speed I'm happy to answer. So in most cases, in the default setting, you should see a result within a second. There exist some options, which I mentioned in the run mode, where you can kind of trade off model performance and prediction speed. So the more context you gather, the more model powers you use, this may take up to 2 or 3 seconds. So this is kind of a trade-off you can tune, but in the end, 1 to 3 seconds is like what we aim for, even for the best models.
Great. I can also answer there is a lot of questions around how is the model pre-trained? Does it generalize to different data sets and so on? So we have pre-trained the model on a small number of public data, but on a large number of synthetic data sets. And in these synthetic data sets, we tried to be as kind of comprehensive as possible around data distribution, class imbalances, and things like that. And so far, when applying this model to a number of different data sets from a number of different industries, we have seen that it is working quite well. Of course, we would be very excited for you to try it out on your own data sets and give us feedback so that we together learn how could we further tune the pre-training data set, the synthetic data in the pre-training data set of KumoRFM to make it even better and more kind of business or domain agnostic. So that's, I think, the first answer I want to give. And then the second thing people I see are asking a lot is about fine-tuning, or making the model kind of specialize on your data, specialize on your task. And basically with that you get 2 benefits. So fine-tuning or training from scratch is possible. We support that. We see another very healthy kind of double-digit lift in accuracy generally. And more importantly, it allows you to train smaller models which are now task specific, your data set specific, which means that the inference becomes much more scalable, becomes kind of computationally cheaper, the response time is shorter, and so on. So yes, Kumo supports fine-tuning or training custom GNNs or graph transformers on your private data for your private tasks. Of course, that requires a bit more work. It's not in context, but it gives you a healthy lift, and computationally it's cheaper.
Okay, there's one more question around like an LLM interface. I see that coming off quite frequently as well. So far, KumoRFM supports predictive query language, which is like a super deterministic and declarative but exact language to define a prediction task, which is what we feel is the most best way to start this. But obviously, you can think about LLM wrappers or MCP interfaces, and that will follow up pretty soon on our end.
Great. I can perhaps go go down the list and keep asking questions. There was a question about the prediction speed. We are going to continue publishing research papers. We are going to keep you updated, and going forward, we are going to release other kind of more powerful versions of the model. We are going to keep supporting this SDK, and we are going to keep kind of the free tier of RFM going forward. We don't, like, honestly speaking, we think that the free tier is great for experimentation, is great to get a sense of accuracy and what this technology can do. If you want to use this for production level use cases, you are going to hit rate limits and things like that. So that's a good time when you can reach out to us and we can have a commercial discussion where we can, provide you guarantees with uptime, with increased scalability, increased rate limits and things like that, so that you can really kind of serve your application and get the value out of this model.
Shall I take one more if time allows?
Yeah, let's keep going.
Okay, there's one question around cold start and how KumoRFM works in cold start scenarios. I feel like this is a problem that spans over all machine learning, where cold start is a problem because you can only predict so much with the limited amount of information you have. I feel like the whole relational deep learning concept is pretty well suited for cold start problems because all the entities you're using as training nodes or in KumoRFM as in-context learning nodes were a cold start node previously in time. So since we're gathering training labels from historical snapshots, it's natural to think that we're also training on a lot of cold start users to begin with. And we don't see any issues so far on cold start problems in our evaluation. If you hit any, let me know.
Great. Another question I see, Net is very interested. So he's asking about how scalable is the model, how much data can you pass to the foundation model, does it have its own hyperparameters, and so on. So in terms of scalability, right now the model we have released supports, I think, up to 10,000 in-context learning examples. So the free version has 1,000 in-context learning examples. Of course, you can put in less. The commercial versions allow for more. They allow for further scalability. As I said, up to tens of billions of nodes and bigger kind of context windows or training data sets. In terms, another question I think, Nat, you were asking is about inferring primary foreign key relations. I think people are kind of asking what is our assumptions around the data? Fundamentally, we make two assumptions. We make the assumption that the operator, the user, knows what data they want to use for learning, so what tables they want to use. So you have to kind of select the tables, between 3 and I don't know, 10, 20 tables. You need to tell us that user ID in that one column in one table is user ID, and some other column in some other table is also user ID. So you need to tell us what points to what. So we assume that you have some kind of IDs relations between these tables. And the second thing we assume is that your timestamps are reliable, right? We truly rely on the timestamps of the events so that when we create this contextualized subgraph, we know what is the time of now, what is present, and then from that present we can say you can look at all the events that come from the past, but you cannot look at the events that come from the future. So your timestamps in the data need to be reliable, because with this we prevent data leakage. But if your data timestamps are unreliable, then you don't know which events happened in the past and which events happened in the future. So these are the two assumptions. Your data can be kind of messy. It can have errors. It can have missing values. It can be incomplete. It can have a bunch of nulls. That is not a problem. It can be noisy. It's also not a problem. The two things we count on is that user ID in one column in one table is user ID in another table, so you know how these columns relate, and that you have accurate timestamps. Matthias, you want to take one more?
I can't find that many anymore. There's one question on whether KumoRFM is only for normalized data, or whether it can also integrate contextual text and so on. So in the end, KumoRFM is pretty diverse in that sense. So yes, you have the restriction to speak through predictive query in that sense, but predictive query is a powerful language that allows you to define many different business use cases. So if you see a limitation in predictive query where you fail to formulate a predictive problem, we are super eager to add this into predictive query. On the one hand, there's like an alternative way to kind of bypass predictive query and use like a custom training table or custom context table where you can formulate any predictive problem yourself. I would recommend from using that, but if you hit any limitations in formulating your problem with predictive query, feel free to contact us on GitHub or on Slack or wherever.
Okay, thank you. So we've reached the end of our workshop. Thank you, Yura, and thank you, Matthias, for sharing knowledge and practical examples. And thank you, all of you, for joining and for your amazing question and positive comments in the chat. For any question we don't have time to address live, we will follow up via email, and I hope you gain valuable insight during this webinar. Tomorrow, we will send you an email with the video recording and all important links that we've shared on this webinar. Thank you once again for your time and attention, and have a great day.
Yeah, thank you, everyone. And please give us feedback and let us know how this works for you and for your use cases. Appreciate it. Bye-bye.